Good afternoon. On behalf of Preferred Utilities and Dave Oaf and myself, thank you for participating in today's webinar. Our contact information is on our website and on this slide. Today's topic is reducing boiler emissions and achieving sustainability goals. In this case, the egg came first, with the Clean Air Act being established in 1963 to study and clean up air pollution. In 1970, a stronger Clean Air Act was implemented and the EPA was created to enforce the law. In 1990, authority was expanded to enforce the regulations and the establishment of the National Ambient Air Quality Standards. And they followed 6 common air pollutants: particulate matter, ground level ozone, carbon monoxide, sulfur oxide, nitrogen oxides, and metals such as mercury and lead. Primary standards set limits based on human health, while environmental and property damages are addressed in secondary standards. Areas that are cleaner than the primary standard are called attainment areas. Areas that exceed the primary standards are non-attainment areas. Ozone and ozone transport. Ground level ozone is formed from VOCs, volatile organic compounds, and nitrogen oxides. Primary sources are cars burning gasoline. Other sources include chemical plants, certain chemicals, and power plants. Geography and location play a large role in a city's GLOW, or ground level ozone, or smog. That's the reddish-brown tint you see over some cities. But it can be influenced by lay of the land, temperature inversions, and upwind contributors. For example, New York City metropolitan area has a large problem, and that's led to the formation of the Northeast Mid-Atlantic states, forming the OTR, or Ozone Transport Region, and they've accepted more aggressive limits to their emissions. So these are the Clean Air Act National Ambient Air Quality Standards table. You see carbon monoxide standards of 9 ppm, nitrogen dioxide, primary standard of 100 parts per billion, ozone, particulate pollution, and sulfur dioxide. The limits can be lower in certain regions, but cannot exceed these national standards. If you ever notice a spec or documentation, quite often is expressed in pounds per millions BTU. This is the way you convert from parts per million to pounds per million BTUs for the various fuels, as well as for the chemicals, the pollutants that we are going to be talking about today. So this is a handy chart to print out and save. Surveys show that the public perception is we are emitting more today and air is getting much worse. Despite this overwhelming perception, the U.S. is doing quite well. And actually the developing nations are contributing to most of the world's pollution. As you can see in this table, the EPA is tracking air quality from 1980 to 2018. Carbon monoxide emissions have gone down by 83% in those 38 years. Lead by 99%, primarily through taking lead out of car fuel, gasoline. Nitrogen dioxide is down by 65%. Ozone is down by 31%. They didn't collect particulate matter data back then, not until 2000. And sulfur dioxide emissions are down by 91%. Here's another way to look at it, a nice, little easier to look at graph, where the center line of the x-axis is the most recent national standard. As you can see, all the various pollutants are tracking down and are considerably below, most of them are considerably below the national standard. The U.S. Nox air quality from 1980 to 2018, as you can see, we're above what is now the national standard of 100 early on. but about the early 2000s, we dropped below that standard, and today we're quite a bit below that. And that's measured daily max 1 hour averages. Since most of us are in the Northeast, this is a graph showing the Northeast emissions from 2000 to 2018, the same daily max 1 hour average. So that's a 34% decrease in the regional average. There are three main ways to reduce emissions. There's pre-combustion choices, there are combustion methods, and then there's post-combustion methods. We're going to discuss those separately. Fuel selection is one of the most important factors in minimizing emissions. As you can see, these are expected emissions of NOx and carbon monoxide from natural gas combustion combusted in various types of boilers. Large wall-fired boilers, small boilers, tangentially fired boilers, as well as residential furnaces. The emission factor rating simply indicates the quality of the data, the number of sample sets that they have to back this data up. Another table here. These are emission factors for the criteria pollutants and greenhouse gases from natural gas combustion. And those are listed, carbon dioxide, lead, NOx, particulate matter, sulfur dioxide, total organic compounds, methane, and volatile organic compounds. Now, most of these statistics you're going to see are going to be corrected to 3% oxygen. So it's very important that you do that, and not very many installations are right at 3%. So when you look at the raw data, you always must correct it to 3% oxygen. David, is that wet or dry oxygen?
It really doesn't matter. If you're measuring NOx wet, you would use your wet O2. If you're measuring NOx dry, you would use your dry O2.
Okay.
As long as you're consistent, the formula works.
It is important to note that combustion has pass-through components. Pollution from sulfur, lead, mercury, and particulate matter are not influenced by combustion technology. They're in the fuel and pass through the combustion process. Table 1.3.1 shows various fuel oils emissions, expected emissions for SOx, NOx, and CO for different size types of fuel oils. And it's important to see the differences in residential furnace, as well as the previous slide, the natural gas emissions. So far, we've discussed pre-combustion techniques to reduce emissions, mainly fuel selection. Next, we'll talk about operational changes, but I want to take this time to point out the EPA website and the wealth of information that's available there. Earlier, you saw air trends that came right off of the EPA website, and recently just saw the statistics on fuel characteristics, and all this and more information is available at epa.gov. So next we're going to start talking about operational changes to reduce emissions. Obviously, there are things like good boiler tuning and lean excess air that can improve performance and efficiency in any operation. But mainly we'll be discussing the reduction of pollutants that are not pass-through pollutants, but optimizing combustion and efficiency by improving the combustion process. So focusing on NOx emissions, NOx is usually 97% nitric oxide and 3% nitrogen dioxide, but it is formed in three distinct different ways. It can come from fuel NOx, thermal NOx, and prompt NOx. Fuel NOx is oxidation of the nitrogen molecules attached to the hydrocarbon chains inside the fuel. The thermal NOx is NOx formed by disassociating nitrogen molecules in the air that join with the oxygen in the air to form nitric oxide. So two distinct different areas and sources for the nitrogen. And finally, prompt NOx. which is formed from the rapid reaction of atmospheric nitrogen with hydrocarbon radicals. Now, I wanted to insert here where we've seen pollutants characterized in a few different engineering units. When you see pollutants characterized as parts per million, it's important that you correct for the oxygen level in the stack, because it influences the statistics. You take the formula shown here, actual NOx times 20.9 minus 3 divided by 20.9 minus your actual measured oxygen. And this works for CO as well as any of the other stack pollutants. Fuel NOx reduction, oxidation of the fuel-bound nitrogen molecules that are attached to the hydrocarbon chains. Single burner fuels, the only way to do it is by burning cleaner fuels. Multiple burner boilers, larger boilers, can use fuel staging techniques to reduce NOx. And the approach there, the strategy is to convert the hydrocarbon fuel to carbon monoxide in a sub-stoichiometric or fuel-rich environment, and then convert the CO to CO2 and water vapor in a high excess air environment. This can be done in utility boilers through burner tuning over fire airports and putting some burners out of service. Obviously, these methods are not available in a single burner boiler or furnace, and the only way to achieve that is by changing the fuel. Thermal NOx reduction. The dissociation of nitrogen molecules in combustion air follows an Arrhenius relationship, which means the percentage of nitrogen molecules broken into nitrogen ions has a logarithmic relationship to temperature. So to reduce the thermal NOx, combustion engineers reduce the peak temperature of the flame. This is done with burner fuel and air staging to slow combustion and flue gas recirculation that spreads the enthalpy of combustion over a higher mass flow denominator and lowers the oxygen content at the flame so that more nitrogen radicals reform with other nitrogen radicals to make a diatomic nitrogen again, reducing the concentration of oxygen in the combustion zone, increasing the concentration of nitrogen in the combustion zone, reducing the peak combustion temperature, and reducing the amount of time that the combustion gases remain at the elevated temperature will reduce thermal NOx formation. This is a schematic of internal flue gas recirculation, and it's a smart design of the burner nozzles and a swirler. FIR is a NOx reduction technique applicable to boilers that burn gaseous fuels only. It is similar to FGR, except that a portion of the flue gas is mixed with the fuel instead of the combustion air. Use of this technique has several advantages. It lowers the peak flame temperature, reduces the oxygen concentration in the combustion zone, improves the fuel-air mixing, and reduces the time under NOx formation conditions. When the same volume of flue gas is used, FIR can be more effective at reducing NOx than FGR. To minimize possible confusion, caution should be exercised when the acronym FIR is encountered because it is used to represent both fuel-induced recirculation and forced internal recirculation. This schematic shows external flue gas recirculation, which accomplishes the same type of a thing by reducing the temperature, the combustion temperature. And it is just the external feeding of the flue gas from the stack or the last pass of the boiler back into the combustion air, and where it mixes in the fan or the wind box and is reintroduced into the furnace. It is very effective against thermal NOx formation, but this technology is a little bit older and it goes back to the 1980s. Prompt NOx. The most effective NOx emission control strategy is one which NOx formation is reduced as much as possible and boiler performance is affected as little as possible, except in advanced burner concepts where air and fuel are premixed. Combustion at either low or very high excess air levels results in low NOx formation. For most low NOx boilers, the best combination of low NOx formation and high boiler efficiency occurs when the amount of oxygen is just enough to ensure complete combustion. Operation at very low excess air levels can cause problems. It can result in incomplete combustion and the formation of CO that causes boiler efficiency to decrease. In addition, it can create unsafe conditions inside the boiler that can lead to an explosion. CO emissions reduction. CO is caused by incomplete combustion. CO emissions in a typical boiler or furnace realistically always less than 10 parts per million. CO emissions are caused by fuel-rich combustion, not enough air to mix with the fuel, and too lean a combustion where there's too much combustion air. And it can also be caused by flame impingement on the tubes or the furnace wall or cool refractory. The flame could be too small, so it's not getting above the critical 1400 degrees Fahrenheit. It is much more common to have CO emissions at low fire than at high fire. So, in summary, we've got NOx abatement methods. Fuel NOx, use a cleaner fuel. Thermal NOx, reduce your peak flame temperature. And prompt NOx, improve mixing and eliminate rich zones. And post-combustion treatment, which we're not going to discuss today, but just so you know, and it's also available on the EPA website, SCR and catalyst beds and chemical injections, and that area is really developing quite rapidly in the last few years. So with that, I'm going to pass the baton over to Dave Oaf, who will talk about carbon reduction strategies in the boiler room. Dave, the floor is yours.
Okay, so I'm Dave Oaf. I'm the sales manager at Preferred Utilities. I have been a burner combustion engineer since the early 1990s, and I actually worked in Southern California where low NOx technology really started with Rule 1146 that mandated that if your boiler didn't have a low NOx burner on it, you had to trash it and install a low NOx burner. So we were very busy retrofitting boilers to low NOx burners in the early 90s. And as those slides from Peter show, we've done a very effective job at reducing NOx emissions in the United States. So much so that when fossils like Peter and I talk about emissions, we assume we're talking about NOx and CO and SO2. It seems like anybody under 30, they don't know what air pollution really is in the United States. So when you talk to them about emissions, they immediately start thinking about CO2. And CO2 is what we're going to talk about now, and how you can reduce CO2 emissions in the boiler. So we're going to start small and end big, beginning with fuel efficiency improvements you can make in the boiler room. So it stands to reason that if you burn less fuel, you're going to release less carbon. And we've been using various technologies over the last 30 or 40 years as fuel prices have increased to increase the efficiency of burners for the economic payback. But by decreasing the amount of fuel you burn, you also decrease the amount of CO2. So what you can do, you can retrofit to a high performance burner that will lower excess air, increase burner turn down, and if you employ a control system known as oxygen trim, you can lower your real world excess air or your operating excess air even further. So efficiency gains of 5 to 8% of fuel consumption are possible, and that corresponds to 5 to 8% carbon emission reduction. Another thing you can do is you can reduce the amount of electricity you're consuming in your boiler room. We do this by replacing across-the-line motor starters with variable speed drives. And usually we will start with the biggest blowers or the biggest motors in the boiler room, and that's usually the forced draft fans on the burners. We might put VFDs on the induced draft fans, and sometimes we'll put VFDs on the feed water pumps. But typically we start at the largest motor because that's where the ROI is the most, and that's the FD fan. And the conversion between electricity and CO2 depends on where you are. And the way to calculate this is to go to the EPA's website. They have a calculator there called AVERT, which is an acronym for something or other. The national average is you release 7.07 times 10 to the negative fourth tons of CO2 per kilowatt hour reduced. That number varies from place to place depending upon how much fossil fuel is used to create electricity where you live. So the way the VFD works is by reducing the fan speed at lower boiler horsepowers, you reduce your electrical consumption. And this chart shows combustion airflow versus boiler horsepower. The top line is a traditional burner with an across-the-line motor starter that is somewhat analogous to driving with your foot on the gas and your foot on the brake at the same time. We run the fan at 60 hertz and we throttle it back with a damper. When we put a variable speed drive on the FD fan, we'll use a little bit of damper control at low fire, but the goal is to get that damper open as quickly as possible as you move up to the higher firing rates. And then once the damper is full open, then we start increasing the VFD speed. So that gap between the top curve and the bottom curve is your brake horsepower or electricity kilowatt hour savings. So this is the equation you use to calculate electrical savings for different VFD speeds. It's 1 minus your actual speed divided by 60, all that to the third power. So if you run the FD fan VFD at 30 hertz, your electrical savings is 87.5. At 20 hertz, the electrical savings goes to 96.3. So there's a lot of electrical savings to be had by slowing down your fans. And the conversion, just as a reminder, is 7.07 times 10 to the negative fourth tons of CO2 per kilowatt hour reduced. To estimate the fuel and electricity efficiency gains possible with a burner and controls retrofit, you can use Preferred's online energy saver payback tool. You input the excess air, stack temperature, and load profile of your existing burner, as well as the performance of the proposed new burner, and the web app estimates your fuel, electricity, and carbon savings. You can input your fuel, electricity, and retrofit costs, and the web app will out an ROI for the upgrade. The web app doesn't calculate CO2 savings from the electricity reduction yet, but it's on our list of things for our programmers to do. But for now, you can use the AVERT calculation for your region. So the second strategy you can use to reduce your CO2 emissions is to switch from one fossil fuel to another, switching from a very carbon-intensive fossil fuel to a less carbon-intensive fossil fuel. And this chart shows the pounds of CO2 you produce per million BTU of different fuels. And natural gas is the lowest, and different types of coal are the highest. So I made this chart to show you what the percent reduction in carbon is switching from one fuel to another. So you start in the first column there. If you're switching from number 2 oil and going to natural gas, your carbon emissions reduction will be about 28%. And this is just based upon the stoichiometry of burning the different fuels. And if you remember your high school chemistry well enough, you can write out the stoichiometry equations and check me. All central steam plant boilers can be converted to natural gas firing, including field-directed water tube boilers, packaged water tube boilers, and packaged fire tube boilers. In most cases, new burners and controls will be required. So, burner retrofits require expertise in combustion and boiler controls for best results. In most cases, the burner will have to be replaced. Sometimes a new burner insert can be made to fit into the existing windbox. This video shows a crew replacing the burner in a trademarked Cleaver Brooks boiler with a new preferred burner. As you can see, with guys working really fast, this was done in 41 seconds. This was a fuel switching project at Bates College where they switched to a renewable fuel and achieved 82% carbon emissions reduction but I'm skipping ahead. When you're doing a burner retrofit, it's important to include a vendor knowledgeable in both burners and controls that will walk the boiler room with a representative from the plant and make a replace or reuse decision for each of the following components: the Windbox burner fan assembly, the flame safeguard fuel air ratio controls, instrumentation including pressure and flow transmitters, motor starters, and VFDs. Why spend money replacing perfectly good equipment if it will work with the new burner? So the final carbon reduction strategy we're going to talk about is converting from a fossil fuel to a renewable fuel. And the idea with renewable fuels is we are taking carbon that was already in the biosphere and burning it. We're not taking carbon that was 8,000 feet under the ground in the form of fossil fuels and putting that into the atmosphere. So when we talk about landfill gas or digester gas, or some of the liquid fuels are going to come up in a few slides, this is carbon that was recently trapped, and we're putting it back into the atmosphere. We're not taking long cycle carbon from the dinosaur period and putting it into the air. So everybody in the boiler burner industry is familiar with landfill gas and digester gas. Both are renewable fuels made from renewable sources. We've been burning these fuels since at least the 1980s. The problem is they're gaseous fuels that can't be economically transported any distance. And even if you had the real estate to put in a lagoon or a digester gas in the middle of your campus, you're not going to want to do it because of the smell. Preferred works with two suppliers of liquid fuels. Ensign manufactures a fuel called Renewable Fuel Oil, or RFO, and REG manufactures a fuel called biodiesel residual oil. Both of these fuels are liquids, so they can be put on a truck or they can be put on a rail car and delivered directly to your facility from where they're made. This unphotoshopped picture is proof. So Ensign makes renewable fuel oil, or RFO for short. It's made from tree trimmings from harvest residues or commercial tree plantation thinnings. If this biomass wasn't made into RFO, it would be burned or left to decompose, and the CO2 would have hit the atmosphere soon anyway. RFO has been approved for all regulatory credits for renewable fuel oils, including RINs and RECs. This is a very simple diagram explaining where RFO comes from. The end products are liquid smoke, renewable feedstock sold to petroleum refineries, and RFO for steam and hot water plants. By the way, when you burn RFO in your boiler, it produces a very nice wood smoke aroma. RFO is considered to be biogenic. So greenhouse gas emissions from RFO are about 88% lower than number 2 oil and 82% lower than natural gas. Virtually any fire tube or water tube boiler can be converted to fire RFO. RFO is acidic, so everything in contact must be made out of stainless steel. The greenhouse gas emissions reductions for this fuel, it's not 100% because it does take some fossil fuel to make the renewable fuel and to transport it to the plant where it's going to be burned. Ensign, the manufacturer of RFO, typically amortizes the cost of the fuel conversion in a 5-year fuel contract. Even with the fuel switching costs, the price of RFO is close to the price of natural gas on a comparable BTU basis. Preferred has converted boilers at 3 facilities to RFO: Bates College, Youngstown Thermal, and a CRNC facility in Ontario, Canada. So the video I showed you earlier was Bates College. They've converted 2 of their central steam plant boilers to RFO. As soon as our technicians finish tuning up the new burners, Bates issues a press release touting their success reducing greenhouse gas emissions at their campus. The URLs are there, or you can Google the words Bates and renewable and you'll find these articles. Actually, last summer, Bates announced that they are greenhouse gas or carbon neutral, mainly because of efficiency improvements to the campus and converting their central steam plant over to RFO. Preferred is also working with REG, the nation's largest supplier of biodiesel. They make a fuel called biodiesel residual oil. Think of bioresidual oil as the number 6 oil of biodiesel. It has the appearance of dirty French fry oil, but it has actually undergone extensive cleaning to remove impurities such as ash, heavy metals, and water. Preferred started burning bioresidual oil in our two shop boilers in June 2 years ago. The burner on the left is a 1950s vintage Preferred rotary cup burner designed to fire number 6 oil. The burner on the right is our state-of-the-art low-emissions Ranger burner. They are both burning bioresidual oil. This is the startup data from one of the two boilers. Important things to note include bioresidual oil needs to be heated to 160 to 165 degrees F. If the existing burners that you're trying to burn bioresidual oil in are using number 6 or number 4 oil already, they will have a pump and heater set that could be reused. Note, the combustion efficiency is similar to number 2 oil. Stack CO is less than 10 parts per million. This is considered clean combustion for any fuel. Opacity was 0 throughout the boiler load. In fact, these burners were firing number 6 oil before we changed them out to bioresidual oil. It took no new equipment, not even a new oil tip, to burn the bioresidual oil. Preferred's two boilers have been firing bioresidual oil all through the 2018-2019 heating season and the most recent 2019-2020 heating season with no unplanned downtime. We shut down these boilers each summer, we open them up, and we've found no unusual ash or sooting of the boilers. We fired them up again last summer for a show and tell with no issues at all. The price of bioresidual oil is generally less than number 2 fuel oil. Fuel switching costs vary widely depending on the existing combustion equipment. So the ideal bioresidual oil candidate is a facility that already has a pump and heater set, so already firing number 6 or number 4 oil. They can reduce their greenhouse emissions by up to 80% and spend less for fuel than number 2 oil. There are a lot of facilities in the Northeast that are still burning number 6 and are planning to switch to number 2 in the near future. These plants can switch to RFO or bioresidual oil and exceed all existing and proposed carbon emission reduction goals. So that's my part for reducing carbon emission in your boiler room. We're going to go live now and take your questions. You can email your questions to Peter Knopf, or you can put your question in the chat and we will take them there. And thank you for attending.